Okay, I'm really glad that you got Pair View to work, and so that's cool. I saw the pictures; it's awesome. Let's do just this lesson 2 and walk through the files of openfoam. Okay, so tutorials, lid-driven cavity. So here I am at CFD Direct, openfoam users guide, and let's just go to 2.1, the lid-driven cavity flow. So it's just flow. It's just this. I don't really know what they mean by the lid-driven cavity. So, but it's an incompressible flow problem. It's icofoam. And the icofoam and simple foam are the two that I've used the most here. Okay, so let's do this step first, right? So if we go to, if we do this, step 1 is to get this tutorial from the tutorial directory in my run directory. So I go cd $foam run tp-r, r for recursive, all the auto directories as well. Foam tutorials incompressible icofoam cavity to here. And so cavity's there. So 0 is where the initial conditions for this CFD solver are. Constant gives you the various constants that you need, mainly viscosity. And system gives you all the system things, including the geometry in it. And so that's what this tutorial is about. This tutorial helps you go through the process. So mesh generation. So here's the mesh, right? So X and Y are always in the XY plane on the screen that we're always talking about, and Z is always in the direction coming out of the screen. So that's always the case in, I believe, in openfoam, X, Y, Z. And if you draw the cavity here, it's got 4 vertices. It's got 8 corners, and they're labeled as follows: 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that's the geometry of this problem we're going to solve. And so where is that geometry talked about, right? So block mesh, when we run block mesh, it's going to take the information of the general geometry and convert it into that grid, right? So in here it says in system there's this file block mesh dict. So I'm going to go in system, cd system cat. I use cat, but you can also use more. Let's use cat block mesh dict. It prints it all the way out, but you can just scroll up and look at it. So with cat, I forget what cat stands for, but anyway. So this is this file block mesh dict, and this is it here also on the also in there. So here are the vertices: 0, 1, 2, 3, 4, 5, 6, 7. So if you go back and you look, that's X, Y, and Z coordinates for all the different vertices there. Cool? And then you made a block. I don't know what hex means, and I don't know what all this stuff means. So this is all has to do with the grid generation. So I think you learn that in chapter 4 of this thing. We don't really need to know that. Probably all we can do in this early stage is just copy, just fake our way through that. So there's one block, and the block is the fluid inside that cube, right? And then there are no edges, so then the boundaries. So if we look at the faces, so there's one moving wall, and it's the face of that wall is 3762. Let's go back up to this picture and say 3762. So the water's coming in here. That's what's happening, I think, or the wall is moving there. And then the fixed walls are these 3 walls are fixed walls: 0, 4, 7, 3, 0473, that's a fixed wall. 2651, that's a fixed wall. And by the way, you have to do it in the right order so that 0473, you got to go around this way, and you got to go around this way for the other wall. So that's actually something we got to learn how to do in chapter 4 about how to declare these walls, these different faces. And 0154. 0154. So these bottom three are fixed walls. This is a moving wall, right? And the front and back are they're empty. So that means they don't. That means it's a plane of symmetry, like it's infinitely large in either direction. I believe that's what that means. So this is a one-dimensional. I think this is a two-dimensional problem. So that's where in this file is where you define the geometry of whatever system you're trying to do. This file block mesh dict. So when we're making our own, that's what we're going to look at. We're going to make all the moving wall boundaries. So we're going to make a cylinder. We're going to have flow through a cylinder coming up here. We're going to try and do that. That's going to be the one I'm going to try and do with you right after this tutorial. Good so far? Yeah. So block mesh dict is one, and then when you run it, it calls block mesh dict. So block mesh is a program, and the inputs to that program, the input file, the parameter input file is block mesh dict. Right, and that's a common way that openfoam does stuff. Oops. Okay, so you have to run it from cavity, not from system. So that's a mistake I made. Okay, so then comes the physical properties. So there's two types of viscosity, mu and nu. And the units of nu, which is called the kinematic viscosity, believe me, you'll learn all this stuff in transport, is meters squared per second squared. And so nu is reported as 0.01, I think that's water, and the units are kilograms meters second, time, kilograms meters second, grams centimeters second, and then something else. So that's how this feature works. So it's 0.01 meters squared per second, and that is in that's in 0, I believe. Is it 0 or is that in, where is that? Transport properties. So cat transport properties. So mu is in transport properties, and that's in the constant subdirectory. Again, there's 0. That's the initial conditions. System. There's block mesh dict, control dict, a couple other things. In FV and things about the solver, the CFD solver that we're using. So that's in system, and then in constant, there's a polymesh, which is a directory, and then which now was, by the way, which was created when I ran block mesh, I think, and then U is velocity and P is pressure. So those are in 0 are the initial velocity and pressure boundary conditions that we need. So that's all these files that help you run an openfoam thing. There's blah, 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 and all this stuff. So the other one to look at in this is control dict. So if we go to cat system control, and so this says, right, so again, it has all this stuff, object control dict. So it just defines what it is there. And then the type of application you need to run it with is icofoam. So if we went back to Pitts Daily, we would look at the control dict and it would say simple foam there. You start from 0, you had 5, here's all the time control steps and all the stuff to do to make the CFD solver run right. So that's in control dict. And here it is too, right? This parafoam stuff, I'm going to wait till the end for it, right? So I don't want to look at just the grid. I want to look at it all at the end. So that's what I'm going to do there, right? So then block mesh, then you go back in grid cavity. So ico foam solver runs. So just the 20 time points here, or 200 time points, and then paraview, parafoam. Oh. Parafoam. Typos. Oh, so it didn't, so I just stopped the taping because I didn't have that. So I find Xming and I started running. I just ran it. I found it and ran it. And so now it's there. And so now it runs. And so now I can do parafoam. Look at it. Oh, surface velocity. Let's look at velocity. So it's fastest up here. The velocity is going this way in the X direction, right? So if we go back to Ubuntu and look at what the initial velocity was, oops, hang on. I got to close parafoam, and I'm going to open up parafoam in the background. So ampersand. And then rest times apply velocity, and then play it to the end. And so that's the velocity. That's just the magnitude of the velocity. And so if we go back to Ubuntu and look at use of X, right? So the initial value along the moving wall is that flow's going across the wall here. So flow's going across this top wall. This wall's fixed, that wall's fixed, and that wall's fixed. And so flow is going across this, and some of the flow leaks into here. That's what's going on. That's this fixed cavity problem. So that worked. So what I think we maybe do next time, we can go through all the case studies. You can look at the different block mesh dicts and control dicts and all that stuff to see what's going on there. But reality is maybe we should just make one. Or maybe we can try and make one. So I'm going to try and make one and then give you a video of it. How's that?